All right, I'm gonna do a shorter segment for what I just recorded. First of all, it sounded super. I was speaking really slowly, and I guess I just needed some food. So these set of thoughts were, I guess you could say, kickstarted when I started reviewing some of the work published by Dr. Chandra Wickramasinghe, who is a astrophysicist, astronomer, and mathematician of a Sinhalese background. He's lived a fair bit of his life in the United Kingdom, and I believe he's a dual citizen of the two countries, so Sri Lanka and England. And Chandra Wickramasinghe used to be a doctoral student of Fred Hoyle, I believe. So now I'm not going to get into the wider discussion with regards to who Fred Hoyle was. Again, it's really kind of spoken about in one of the previous videos, or what were some of Fred Hoyle's theories with regards to his rejection of the Big Bang theory, a coin he actually termed, and I will talk about panspermia. I will talk about panspermia because I suspect there's something to this theory, and I'm gonna try and explore just that bit in this shorter segment. I have a little longer segment of this video, which I may or may not release because I sound so like I'm talking so slowly, and it wasn't like I didn't properly prepare for that video. But yeah, so without going to like all of the theories and all of the ways Fred Hoyle had to look at the ways, I haven't like looked into the extensive work done by Fred Hoyle or even Dr. Wickramasinghe himself, so I'm not going to speak too much about that. But I will share my thoughts on what's going on with the search for exoplanets and hypothesize how the panspermia angle could potentially play into this. So first of all, one of the first things I noticed, and this is not the first time I've noticed this, but if you look at the just the Wikipedia page for the Kepler Telescope, then you'll notice that this is how many. This is I don't know when this was last updated, but when it comes to the search for exoplanets, primarily it has been TESS and Kepler. So. Where's my search bar so I can see it? There we go. And test. So yeah, it's primarily there could be other missions by other space agencies, but for the better part, based on my understanding, it's been Kepler and TESS. The Kepler mission named after Johannes Kepler, I believe, and I have no idea what TESS stands for. Kepler was an interesting guy. I believe he was a math teacher, and I'm not sure how true this is. This is very off topic, but he would like just kind of start daydreaming in the middle of a teaching session. He would start thinking about the planets and the relative motion of the planets. I think that's one of the reasons why Kepler is so famous. I could be wrong, right? But yeah, anyway, so yeah, that's what the Kepler telescope's name. That is who the Kepler telescope's named after. Let's take a quick look at TESS. What is going on with TESS? Transiting Exoplanet Survey Satellite. Also operated by NASA MIT. It uses the transit method in an area 400 times larger than the covered Kepler mission. Interesting. So is it okay to assume that as more time passes by, we're going to be seeing more data coming in from TESS versus Kepler? Time will tell. Time will tell. Oh, Kepler has been retired, so it makes sense that I don't know. I would like read through all of the details to TESS, but TESS is going to pick up where Kepler Space Telescope left off. I'm thinking based on the information that I'm seeing from them. Right. So good mission, almost 10 years, planned for 3.5 years. So, wow. It's that's 200%, right? 180%, something like that. If I did my math right, it's a good return on investment there. Okay, so yeah, before we get into the search for exoplanets. What is an exoplanet? Like, I don't know if I covered it in this video, but my understanding of an exoplanet was something that sits in the habitable zone, right? So where is a good image of the habitable zone? I think we have one here somewhere. Yeah, here we go. So if you have you have to appreciate the stellar, like the stars are of different kinds, and it's at different stages of its evolution. I would think this is a younger star, and as it grows older, it loses mass and becomes kind of like a red dwarf or something like that. But contingent on like what the distance is from the actual star, you may have a planet in a particular zone, which is known as the habitable zone, also known as the Goldilocks zone. And this is a zone where liquid water could exist. It's my understanding of this, right? So my understanding of exoplanets was that exoplanets have to be the habitable zone, but it turns out that's not the case, because an exoplanet is simply a planet that goes around some kind of a star. That's really it, right? Now, as of I don't know as of when, but this is how many. Well, as of July this year, 4,777 exoplanets have been confirmed in 3,534 planetary systems, meaning solar systems, with 785 systems having more than one planet. Okay, that's interesting. So we have 4,000 confirmed, and in this many, well, let's do some math. If I can type. There we go. Okay, so 477 minus 3534. So, minus 785. 458. Why is there a difference? Oh, that makes sense. Okay, that makes sense. So you have, actually, this should be the other way around. 3534 minus 4777. Yeah, okay. So you have an excess of, it's not a one-to-one mapping, obviously. If you have this many, so yeah. So when they say 785 systems have more than one planet, this is what the remainder is. So this could be one more planet in a particular solar system out of this number, or two more planets, right? So my math wasn't particularly very keen here, because we have 4,777 confirmed exoplanets. I went with another information. I went with a sample size of what Kepler observed originally, right? Kepler observed this many stars and detected 2662 planets. So what I did was I just put those, I guess I was trying to find the ratio, and I just did a simple calculation to be able to figure out if 500,000 stars were actually surveyed, or solar systems, then if we found exoplanets, and what does that number represent? And based on the data from Kepler, that number comes to around 0.5%. So of all the sample, like the sample size that Kepler explored, 0.5% of that entire data set has exoplanets. That's what it comes down to, right? So let's take a look at TESS now. I think this is where I want to go. Is there any data? No, launched 2017. I don't know what's going on here. I think we want to. That seems a little vague. 85% of the sky. I'm thinking it was mostly studying planets in the galaxy, right? It's going to be pretty difficult to get good readings from a stellar mass in another galaxy. I could be wrong. I could be wrong. I could be wrong. Oh, that's interesting. They got seed funding from Google. What kind of real estate has it surveyed? Well, what? Okay, Testable service surveyed 200,000 of the brightest stars near the sun. Okay. And Kepler Space Telescope surveyed 500,000 stars. So it's doing less than half of what Kepler did. But that's fine. Oh, this is the region of the night sky that TESS is going to survey. In how many days? That's interesting. I wonder why there's more here. Because that's a prime location, or that's easier to monitor from this region, or both. Okay, I'm not going to go into the details here. Okay. It's quite remarkable that out of this data set, you can actually glean what's going on with these bodies to be able to, like, you're pretty much finding needles in haystacks, kind of, sort of. Because you just take an image, you're like, yeah, well, it doesn't matter. But if you take snapshots of that image in time to see like that change can tell you so much. And that's what's really going on here, which I can explore in the longer video. Man, there's so much space in the universe. If we can just figure out how to get to different real estate, but it's ethics. It's a question of ethics. Like, if you do get there and there's life, what are you gonna do? I don't think we should colonize other planets outside of the solar system, provided no life has been found there. If there's no life, then I don't have any problem. But the thing is, I worry that our probes are not going to be detailed enough to look for life that may be on a different scale, or even bacterial life, right? So this goes back to what Carl Sagan used to say. I think Carl Sagan used to say, if there's indeed bacterial life on Mars, we should just let the planet be, because that's where we were billions of years ago. Anyhow, to come back to the topic, this is what we're looking at in terms of domains of how much has been surveyed, right? And like I said, I just took the data from at least the Kepler mission, and I did some simple it's not even back of the envelope calculations, just simple calculation. The estimates for the total number of stars in the Milky Way is anywhere from 100 billion to 400 billion. And that's the source, right? The first search is a Google search. How many stars are there in the Milky Way? And Google comes back, says 100 billion to 400 billion. But if you do a search, if one of the pages that comes up is this page from ESA, and if you click on that, then that becomes a bigger number. Because this is, I don't know if this is a typo, but it says right here, there are something like 10 to the power 11 to 12 stars in our galaxy. So anywhere from 100 billion to a trillion. Wow. Okay. I don't know if this is a typo again. I'm not sure, but I still went with like really conservative values. I actually didn't go to the trillion value, as you can see, because 10 to the power 12 would be a trillion based on what I'm looking at here. 10 to the power 12 in the galaxy. Am I reading this right? Yeah, I'm not even getting to like other galaxies. We're just talking about one galaxy here. This kind of confusing the way you said it. First, they say for the universe, the galaxies are small representative volumes, which makes sense. I wish this was in another line because they go in universe and then they say, well, the galaxies are within the universe, and then they say there are anything like this many stars in our galaxy, and then they go back to this is how many galaxies there are, right? So it's like you're like starting universe, then anyway. So yeah, I did not factor this in. I went with whatever Google was saying. I don't know why I did that, but I went with Google, and I don't know what ESA's source is. I don't know. I don't know what ESA's source is again. But anyway, so I then extrapolated 100 billion to 200 billion stars in the Milky Way, and based on the data set that we found from Kepler surveyed 500,000 stars, and Kepler detected 2662 planets within that 500,000. So that is again 0.5%, right? So if you then take 100 billion and extrapolate what 0.5% of that will be, then these are the numbers in front of you. Depending on 100 to 400 billion, you're looking at anywhere from 500 million to 2 billion exoplanets. Exoplanets now. So we're looking at 500 million to 2 billion exoplanets in the Milky Way. All right. And this is how we have found, we haven't found that many exoplanets there. First of all, I should do a warning, right? That's not what I'm saying. What I'm saying, there could be that many exoplanets in the galaxy. And this is a conservative estimate. This is a very conservative estimate, as you may realize, because I don't know what source is right. Because if we say 0.5% of a trillion, which is ESA's estimate, then there are 5 billion exoplanets potentially in the solar system. But if you go with Google's estimate, then we're looking at 500 million to 2 billion. And this difference is exponential, I think, because there are, well, it's on a different scale, because there are 1,000 billion in a trillion. All right, if the numbers are not like confusing you enough, let's move on. Well, maybe the numbers are confusing you. It's pretty straightforward math. So I don't think there's any. Now, how to define this? How to define these? Now, there's a couple of different mechanisms, right? So I got to go back to the page for exoplanets. And this is a graph that I kind of keep referring to. I've been looking at this graph since forever. I can't remember when. I think I started looking at this somewhere around here, but definitely this range. But I remember seeing the graph 2014. I'm like, wow, what happened, right? So that's when I think started looking more into things like Drake's equation. I think I started looking into the Sarah-Seager equation around here, and started like breaking it apart around this time frame. Not to sound all that, but anyway, so like this graph represents the primary mechanisms through which exoplanets are found, and we're seeing a lot of green and some red. And these two, this is the two I'm going to focus on because these two methods seem to be the most successful. So I'm thinking because Kepler was shut down here, so I'm thinking this is mostly Kepler, right? I think this is when Kepler was shut down. What was Kepler retired? Yeah. Exactly on October 30th, Kepler was retired. Where was that? Right here. So yeah, so I would think this is mostly Kepler's work. All of this pretty much right here, right? And this, I would think, and then tests came online. I'm zooming. And anyways, the two primary methods are 1, 2. These would be transit and radio. And what this means is, this is what this means. Let me just clear this image. Transit is when it's quite simply when you have a star that has something going in front of it. So when a planet goes in front of the star, it's the light coming from that star drops, if I understand this correctly, right? And so you may have a pattern of light coming from a star system, and then a planet goes in front of it, and the light kind of looks like this, and then when the light's gone, that's what happens. So there's something there's a whole bunch of things you can do by measuring this dip, and this dip tells you a lot about that planet itself, which you can kind of vaguely see in the background. Okay, so that's one thing. That's one thing, right? This is called transit. It's quite simple, and well, at least it's simple in principle. Like I said, there may be a lot of intricacies involved with regards to what you actually start measuring when there is a transit. Now, it is possible that some of these objects are mega Dyson structures, right? We don't know. We don't know because I don't know how much granularity you can actually get when it comes to measuring something that's in transit. This image, this video that you or GIF that it is here is just the moon, Earth's moon traveling in front of the star, the sun, right? But like I said, there could be many kind of systems. Some of them could be artificially constructed, which I'm not going to explore right now. But basically, this is what transit means. And this looks like one of the moons in front of Jupiter. It looks like Io, right? So this simple explanation of transit. And if you want to learn more, you can go to the transit page for astronomy on Wikipedia. This is another. Excuse me, sorry about that. This is another example of what the transit may look like. All right. Now, that's just the same image, I think, of the exoplanets. Oh, there's another method here, TTV. I wonder what that is. Looks like there's more methods listed here than the actual page for exoplanet search. I'm just eyeballing it. The other most successful mechanism is the Doppler shift. And if a planetary body is revolving around a star system, it's going to have a tug on it, because not only is the stellar mass attracting that planetary body towards itself with this gravitational pull, whatever how that works, space-time warp considered and all. The thing itself is also having a pull on the stellar mass, and as it does that, I guess the best example I can think of is like shot put, right? So if you notice, like when the person who's doing the shot put, when the person is, this may be a really bad example. Maybe I don't even have to do that because the thing just kind of explains that. But the person who's doing the shot put, when they are swinging something like this, if you notice, they kind of go like this, right? But that's not maybe that's not a good example here. But anyway, so yeah, it's pretty it kind of explains itself. Now, what happens with the Doppler spectroscopy is that as objects go near, relative to us, if there is a shift towards the Earth, then there's this is called the light. I forget what it's called. It's just called Doppler spectroscopy. But if again the star that you're looking at is moving towards the Earth, then its light, or the wavelength of its light, is blue shifted. So something happens with the wavelength itself, and it shifts to more like a blue shift. I don't really know like how that all works, but light's got different spectrums or wavelengths, and it shifts to a blue shift. While when it's moving away from the Earth, it's red shifted, right? So just right here. And like I said, by analyzing these spectral shifts, astronomers can deduce the gravitational influence that an exoplanet is having on a stellar or on a sun. Okay, so that's how Doppler spectroscopy works, and that is how transit works. And these two, like I said, were pretty successful when it comes to the Kepler mission. So now we're going to see how's it going to change going forward? Looks like this holds true. So test would have come online somewhere here, and looks like I'm seeing a lot of green and red. Well, looks like it's kind of like not exactly the same proportions, but it looks like 2016 was super successful for transit. And that could just be the fact that we may have found most of the exoplanets in that cluster that we are observing. So it remains to be seen what cluster is now going to be observed using which method or which set of methods, and what's going to happen next, right? But I just wanted to come back and point out that this is the minimum number of exoplanets that we are looking at in the galaxy. Okay, so the latest estimates are anywhere from 2 trillion galaxies to a couple of hundred million. No, sorry, a couple of hundred billion, not million, because they say it could be a reflection of some sort. So maybe somebody made a mistake, or that's how, like, I don't know how that all works. But last estimate stood at 2 trillion galaxies. So if I like, just out of curiosity, I'm just curious if I think, again, I don't think I calculated this right. So this is a much lower number, and you have to also consider this 10 to the power 12 by ESA. So do we have a trillion planets, or like what's going on, right? But anyways, I'm going with the data from Kepler, and so now what I'm going to do is I'm going to multiply 2 billion by 2 trillion, because that's how many galaxies there are. 2 billion multiplied by 2 trillion. 2 trillion galaxies, 2 billion planets each in each one of the galaxies. So there are at least, looks like, 4 sextillion planets in the universe. That is 4,000 billion 10 to the power 21. And it's not even on this thing, because this only goes to 10 to the power 2014, right? Okay. 4,000 billion. My question is, if it's in the galaxy, we're looking at 2 billion planets. If it's in the galaxy, right? I gotta, like, hold on, if it's in the galaxy, we're looking at 2 billion galaxy, 2 billion in the galaxy. And if we're talking about the universe, then we are looking at this many planets, universe. And remember, these are conservative estimates, both of these estimates. So what was the number here again? 2 billion, right? 2 billion in the galaxy. I don't have to, I can just denote that with the same, I guess, galaxy 2 billion, 2 trillion galaxies multiplied by 2 billion. This much, 4 6, these ones, 4 sextillion, which is 4,000 billion. My question to you is, do you believe that with this many potential planets in this universe or in this galaxy, do you believe that life only exists on Earth? Actually, it looks like I'm influencing discover what's possible was already there. Do you believe that? Actually, I don't know what the answer is. That's a really bad image of Earth. And South Australia, Africa, Asia. That's bad. Well, that's the best I can draw right now. Do you believe that life only exists on Earth? If so, why? Why do you believe that? Why do you believe that? I was going to talk about panspermia, because I really am suspecting, I don't want to influence thoughts, but I think whatever's going on in, like, I think it seems very it seems very improbable that however life evolved from amino acids turning into nucleotides to forming more complex cellular structures and becoming eukaryotic eventually over the billions of years. I can't see how that could happen only on one planet out of this many. I can't. Like, okay, so just for the sake of a thought experiment, let's say that only happened on in this galaxy. There's still 2 billion planets that are potentially have some kind of a life on them, whether it's bacterias, you know what I mean? Some, like, however that evolved, cluster of bacteria and viruses. You know what I mean? I have no idea what archaea is, if it's still alive. There's flora, fauna, bacteria, and archaea, right? I could be wrong. But I highly suspect that this, at the very least, plus other, maybe there's something else. Who knows, right? I'm not talking about like non-bacterial life, sorry, non-DNA based life, but that's also, I think it should be in the realms non-DNA, right? So non-DNA based, I think the question is non-DNA based. How does it work in conjunction with this, right? And I am suspecting that my question is, like, however the galaxy, at least however things evolved in the galaxy, how did this stuff get seeded from one planet or one star system to another? Uh, that was the solar system. How did that get seeded over from one to another? That is, like so many light years away. The closest to us is 4.x light years away, right? So it takes light this much distance to travel from one star system to another. Maybe this distance was less at some time. Maybe when, like, like stars pass by each other, right? So maybe this distance becomes less, and then bacteria hop. The question is, how would they know? How would they know, right? Even though it becomes closer, it's still, it doesn't go from 4.x light years to like zero point 0.5 light years. It's still, like, significant leap. But the question is, how does this happen? So there's a whole set of questions around panspermia itself, right? I think it makes logical sense to think that it could be more in the domain of panspermia, directed panspermia, which is an interesting thought at the very least. Because now, if we're talking about directed panspermia, then it's not panspermia. So, what is panspermia, by the way? What is panspermia? What is panspermia? What is panspermia? And let me save this image before I lose it. Panspermia is a hypothesis that life exists throughout the universe, distributed by space dust, meteoroids, asteroids, comets, planetoids, as well as spacecraft carrying unintended contamination by microorganisms. Distribution may have happened or occurred spanning galaxies, and so may not be restricted to the limited scale of solar systems, which is exactly what I was talking about right now, right? And this is an artist's depiction of what it may look like, with all my squiggly stuff in front of it, skewing your view. But there's different proposed mechanisms. I didn't go through all of them. And I'm like interested here, like what's happening here, like what could have happened here. And I'm not the first to hypothesize this, as you can see on the Wikipedia page. Francis Crick, along with who's the other fellow? James Watson, right? Uh, Watson and Crick. And Rosalind, I believe Rosalind Franklin was the one who took the first image of a gene, if I remember correctly. But yeah, Watson and Crick helped to did some instrumental work with that was deciphering the helical structure of the molecule. Prior to this, it was very theoretical. Um, so I don't know much about genetics. I'm not going to talk much about that. Very interesting subject, but it looks like they were thinking along these lines. I don't know who Leslie Orgel is. Okay. So yeah, there have been other proponents of this as well. I think Dr. Carl Sagan had some ideas here, which is not on this page, but I don't see it. And while others have had similar theories. Um, well, so I like this is the shorter version of the video. I'm just saying, like, I'm like more interested here at the very least, and I think if there is indeed life that is throughout the galaxy at the very least, then the implication of something like this are profound because we could now have a galaxy. Now, let's imagine this is the black hole that's hypothesized to be in the middle of the galaxy. I say hypothesized because I don't know what I'm talking about. And plus, there's a lot of evidence to suggest there's a black hole, but I'm saying it could be something else, right? But so anyways, if this is the galaxy, then, and if we are somewhere here and we were here 66 million years ago, because we're going at, no, that would be clockwise. So we were here 66 million years ago and we're not here, we're somewhere here. And if stuff's getting seeded all over the place for billions of years, then there must be many colonies of bacteria all over the place, right? How they all interact with each other is a mystery. Is a mystery. My question is, and they're all over the place, so I'm not gonna draw this out right now. I don't know why this stopped drawing. There we go. Okay, they're all over the place. Entire galaxy is teeming with some kind of bacterial life. But the distance are immense. Like I said, there's light years of distance. So can these beings survive across these vast distances for tens of millions, hundreds of millions of years? That is a question that has yet to be answered. I don't know the answer to that question. I have some ideas, but my question is, what if there was some advanced civilization that was, say, thousands, if not millions of years ahead of us? And what if this civilization was sending copies of genetic code for whatever reason in all the different parts of the galaxy, all the different parts? What if, right? Because think about it, think about us. Like right now, the closest thing that the closest we come to that is like the Voyager probe, right? So Voyager Probe, and my thoughts have definitely been influenced by Mr. Chandra, Dr. Chandra Wickramasinghe. But Voyager Probe, he's got a picture of a man or a woman. He's got a couple of songs, and you got hello in like X number of languages, maybe some songs, right? And I think it's Voyager 2. Which probe is that? Voyager plaque. Pioneer. Oh, I'm sorry. It's a Pioneer, not Voyager. I think Dr. Wickramasinghe is mentioned this in one of his paper. Like, if aliens are gonna see this, okay, well they'll see some being here, right? I don't want to remove my images, but that's what the images that this is floating somewhere in the ether of space right now, or in somewhere. I don't even know where it is right now. I'm not going to comment on this. It looks like the original image was different. Anyway, so yeah, well, I think one of the criticisms is like, if they like, how will they play that thing? Like, what medium is that recorded in? Like, you mean? So, anyways, so I think it makes sense that if there was life and it wanted to see the galaxy at the very least with code, that would send genetic material which could survive those long distances. And the question is, how do you propel it, right? At what kind of distance at the speed of light? That's the big question, and that depends on the technological capability of the I guess in this case civilization that we're talking about. So now let's go back to the numbers. So let me save this. It cleared. Now we're looking at like a lower level estimate of 2 billion planets just in this galaxy. Just in this galaxy. We're not going to go with those crazy numbers of the universe. Just 2 billion planets, 2 billion planets at least, right? 2 billion planets. Okay, 500 million. Let's go with the least number of potential planets. We'll do 500 million planets at the rate of 0.5% of the planets that are going around a star. So sorry, you have 100 billion stars and only 0.5% have some kind of a planet around them. So that number comes to 500 million. So now let's go here. So 500 million. What is 0.1% of 500 million? Now let's assume that of all of, you know what, I'm going to make it a really small number. Of all the planets that exist within this galaxy, 0.5%, sorry, 0.01% of them could harbor some kind of life, right? Okay, so that number comes to 50,000. And I'm going to do this again. Now, out of the 50,000, only 0.1% have the capacity to be able to send signals outside of their solar system. So that's 50,000. Five. So we're looking at 5 potential civilizations that have the means and capability of doing what I shared. And this range could include all the way from sending Voyager-like plaques or Pioneer-like plaques to sending genetic code all over the place, like I mentioned. So this was the lowest level estimate. If you tinker with the numbers, you may come up with some other numbers. So if there are 5 potentially, then we are one of them. Pioneer was one. So that means there are 4 others, right? 4 others. These are not literal numbers, please. So the question is, if one of these four are sending code, some kind of code, genetic code, and if they are, then this would be in the domains of directed panspermia. And this is my short update for the same topic. I still put the question out there. What do you think is the probability of life being out there in the galaxy? I'm not even talking about the wider universe or the multiverse or multi-dimensions. We're just talking about the galaxy. At least 100 billion stars, at least 500 million planets in that cluster, in that, I guess, real estate overall, all around the galaxy. We're looking at 500 million planets. I think the number is very high for planets because this one doesn't factor rogue planets. So if you type in rogue planets, this includes planets that have been ejected from a solar system, as well planets that have never been gravitationally bound to a star or brown dwarf. And Wikipedia says the Milky Way alone may have billions to trillions of rogue planets. Arranged with the upcoming Nancy Grace Rowan Space Telescope, will likely be able to narrow down rogue planets. What is this video? Billions to trillions, billions to trillions, billions to trillions. That changes the whole dynamic. That changes the whole dynamic because we now don't have 500 million planets in this galaxy. We don't know. We don't know. This changes everything. This changes this number. This changes everything. We have billions to trillion rogue planets. All right. So billions to trillions. In a trillion, you have 1,000 billion. You have 1,000 billion. Okay. Billions to trillions. Billions to trillions. Oh, maybe that's why ESA said that it could be. No, they said stars. It says stars. Billions to trillions. Okay, so we came up with this estimate of 2 billion. That was stars circling a stellar thing. What about rogue planets? So billions to trillions. Let's go with a lower number. Well, they're saying billions to trillions, right? So 1 trillion, just trillions, they said. 1 trillion again has 1,000 billion. I'm just making sure. Yeah, 1,000 billion. Okay. So let's say we have 10% of 1 trillion. That would be 100 billion. Yeah. No, 10% of 1 trillion. 10% of 1 trillion. If not off. Yeah, simple math. That's going to be 100 billion. Yeah. So 100 billion plus the 2 billion. Okay, let's make it 1% of 1 trillion. Let's say maybe there's a very low number of rogue planets. So it still comes to 10 billion. 10 billion plus 2 billion, right? The question is, how would life be supported in the rogue planets? Because it doesn't have a stellar mass going around it. Who knows? Like it depends on what kind of life you're talking about. We're talking about like some kind of life being supported by underground, like in underground caverns, like you have like shrimp living in the bottom of the ocean, bacterial life, or maybe some advanced civilization at that long left its solar system for whatever reason, and it's now just floating there somewhere because it doesn't need a sun. They have fusion or some other clean tech, and you're just chilling. And they're living in a terrarium of sorts, it's completely safe. And yeah, depends what kind of life. I'm just like interested in bacteria for now. So 10 billion plus 12 billion. 12 billion. This is not good. This is like very rudimentary math that I did in front of you. So we're looking at 12 billion planets where the possibility at least exists for this could be a bad number. Maybe this is not the way you're supposed to look at it, but 12 billion bacterial superclusters, right? So let's see, I'm just kind of curious if there are, how should we do this? Because you have more rogue planets than, well, not more, but 12 billion, and there's again 100 billion. How many are there? 100 billion to 2 billion, 400 billion star systems. Let's say there's 150 stars, right? 12 billion is what percentage of 150 billion? About 10%. So that would be the surface area. I would think of this in the surface area at least. So if this was again the galaxy, right? Something like this, with 12 billion planets, rogue and other planets traveling the it needs some more rings. I just messed it up. Let's try this again. If you have 200 billion or 150 billion stars in this galaxy, and planets circling them, and rogue planets, then you have 12 billion planets that can support life. I think I'm repeating myself, so I must be getting tired. 12 billion. 12 billion represent 8% of this. Like, I don't know how you look at it, because I don't know how this is spread, right? And it doesn't mean that it's spread uniformly. It could be that this could be the region of the galaxy that somehow has this growth. But considering the fact that, hold on, let's think about this. How old is the galaxy? Not LA galaxy. How old is the Milky Way? Okay, around the same size as the universe. How old is the universe? Okay, the galaxy was formed earlier than the universe here. Okay, we're going to ignore that. I think it's just rounded off to 14 billion. Because like the galaxy formed around the same time as the universe. The question is, what happened to the galaxy after the galaxy formed? Was it more crunched? Was it more expansive? Did it shrink? Did it expand? I don't know. At which rate did it expand? Right? These questions are determined, like where were the initial set of stars? This is going to be the hypothesis, like it's also going to be on the assumption that during these 14 billion years, new stars have emerged and old ones have died. Stars have died. How do you do this? This one, like this. Old stars have died, right? And new ones have emerged. Happy ones, right? Different kinds. But the question is, how have these moved? How have these stars moved during this time? How have they moved, right? Because today we have this understanding. So if the solar system that we're in, say, roughly speaking, is here, then 66 million years ago, it was here, because it takes 280 years, 280 million years for this solar system to do one loop. So 14 billion years. Well, let's Google this. I don't know if I'm going into too much detail. Well, it wouldn't have been 280 million years, but 14 billion divided by 280 million. Yeah, this number would have fluctuated, 280 million. Okay, but roughly about 50 revolutions around the black hole. So 50 revolutions around the black hole. So if the solar system, there's just one of the trillion, like the hundreds of billions of solar systems, or at least stars. This star that we kind of circle right now has gone around the galaxy 50 times. 50 times. And as it did so, it may have collided maybe with some other stars, or maybe other planets. Planets collided amongst each other. It may have gone through dust clouds, cometary, like I don't know, remnants of something that another collision may have left behind. And if there was life on these fragments or shard, then the Earth would have come in contact with this. My whole point of this is like my whole thing is, my question is, if life could have survived these enormous distances, right? If life could have survived this enormous distances, because this is not days or weeks. This could be hundreds of millions of years, right? Kind of the hypothesis that is just like mixing and mashing based on however stuff flows through the galaxy. But the other question I also pose is, what if there were 4 other advanced civilizations, and instead of sending pioneer flags, they are sending code. They are sending code. They are sending code, right? And what if this is happening all over the place? What if, right? Maybe there are more than 4, right? And so there must not be a common origin for life then. Then life must be getting mixed and matched all over the place all the time. And I would think with better genome sequencing, you could decipher questions to those answers. But the problem is the sample size that we have is only native to what we know, which is Earth. So how would you actually deduce that something is not from this planet? Yeah, so this is not what I was looking for, but you also have species that's thriving in many harsh environments, in hot springs, in places where water is corrosive, as you can read in this article by BBC. And there's other bacteria that is literally ingesting arsenic. I think they later found out that this wasn't true, and I think they redacted this. I could be wrong, at least the arsenic one. I could be wrong. I think when they're talking about stealing genes, they're talking about horizontal transfer, which I don't know much about. I was reading up on this earlier. So we know, like, these creatures, the bacteria can survive in harsh environments. The question is the distance. I think my image is gone, the one I drew, but the enormous distances. Anyways, this is my shorter video for panspermia. And I'll leave you with a question. What do you think? I don't want to influence your thought with like a picture of exoplanets in the background. But what do you think is the probability? Probability. How do you denote probability? I think with a capital P and a small p, I don't know what the difference is. What do you think the probability is of life in this galaxy, not the universe just yet, just the galaxy? And if you think there is 0 probability, then there's no other conversation, I guess. Let me just switch here so we can read this, right? But if you think that there is some probability, on the other hand, you say, well, X is the probability. Then my question to you is, do you suspect that some of what we're seeing could be directed panspermia? Directed panspermia, whereby a species is deliberately seeding the galaxy with genetic code at the very least. Food for thought. Have a nice day. Thank you very much.